All right, thank you very much. So I am Ken Crooks. I work for ERLAB. I'm the director of the Green Fumehood Filtration Technologies in North America. And I've been here for about 7 years now. And I've been in this industry, the industry of heating, ventilation, and air conditioning, or HVAC, as we like to call it here in the United States, for 35 years. Hard to believe sometimes. But I love this industry, and I've been on the air treatment side for that long. And it's all brought me here to ERLAB, where if you were logged in at the beginning, you understand 52 years of dedication for protecting personnel through chemical filtration in the laboratory. And so today's session here that I'm going to present is choosing containment devices based upon risk assessments, which really is a very logical statement because I can't imagine doing it any other way. How would you know which containment device to choose if you hadn't assessed the risk to begin with? So the agenda will be obviously the importance of a risk assessment, and then talking about how to conduct those, or at least how we do those here. And then after that, choosing the proper safety equipment based on principles, standards, and effectiveness. And you see the different types there that we'll cover. I will focus mostly on fume hoods, chemical fume hoods. That's what the majority of this is about. We could spend more than an entire day talking about containment devices, and I would not be the expert for that. Fume hoods is my life, that's my background, but we will touch on biosafety cabinets, isolators, or glove boxes, as we like to call them, and then very briefly other types of solutions, and then lastly we'll conclude. So why is it we should do a risk assessment? What's so important about understanding the risk anyways? Well, we want to be in the middle. We want to be in the middle of this bar in that nice green zone. We don't want to be too far to the left or too far to the right, because you can either underestimate the risk and then you'll either have not enough fume hoods leading to work done on the bench, or you won't have the right type of containment device. Either of those scenarios is bad, right? Because we'll have exposure, right? We'll have our researchers or our students or our teachers being exposed inside the laboratory. But then on the opposite side, if we overestimate, then you're going to spend a lot of extra money on capital equipment, right? The engineering controls and solutions, and I'll talk about that. They'll consume a tremendous amount of energy. Maybe you're over-ventilating, maybe you're over-exhausting, and that'll lead to a very large carbon footprint. So that balance between the underestimate and the overestimate, and again, being in that green zone in the middle, leads to the most sustainable solution that's also the safest. And I do want to say safety is absolutely the goal here, and then making it sustainable. It is not the other way around. It has to be focused on safety and understanding the risk entirely. So some findings that we've found over the years concerning the protection of personnel, the number of fume hoods rarely corresponds to the real needs of the laboratory. Now, this may not apply for brand new construction or a new renovation, but basically we go out to industry, we go out to schools, and the number of hoods that they have on rare occasions actually meets the real need. Sometimes they can have too many, but usually they don't really have enough. And then the proper use of the safety devices is not mastered all that often. There are people that absolutely understand very safely how to use properly these containment devices, but it's rarely is it actually mastered. And so I'll talk about administrative controls and making sure there's a training program in place to make sure we cover that risk. And then hoods are validated during their installation when they're originally installed and started up or replaced. And then after that, annually, of course, every year, a fume hood should be certified by an independent third-party certification company, not related to the manufacturers or anybody involved with the project, working directly for the owner. But then what happens in between? That's an entire year for this very important containment device to hopefully work 100%. And that usually is not the case. So where is there risk? Right? If we're going to assess a risk, we first need to locate the risk. So when you have a chemical hazard, and again, we're focusing on laboratories and chemical fume hoods, there are many different types of risks. But if you have a chemical hazard, right, that can be caused by toxicity or volatility or reactivity of that chemical. And you also have the chance for exposure. You're working with that chemical in a laboratory. Right? And that exposure will come under many different conditions, whether it's the container type that's used, or you're elevating the temperature, you're heating it, vaporizing product. or the concentration, it's an extremely concentrated version of that chemical, there's some risk. And that risk happens in that overlap, where exposure and chemical hazards overlap. That's where we really identify the risk in laboratories. And so that, again, can be exposed with the chemical properties, the physicochemical properties, the method of using that chemical, right? Whether it's evaporating, dispersing, droplets, it's airborne, obviously is a concern. And then the dose, how much will you be exposed to? In other words, the duration and the frequency of use. So total dose, it may be a low concentration, it may be a low risk, but if you're using it continually, that becomes a larger dose, and therefore that is a larger risk. So examples of risk. Here's three just very simple examples. So if you've got a bottle of acetone, it's closed and it's locked up nicely in a storage cabinet, there's really no risk there. There's a fire risk if the building is on fire, and so therefore you have a fireproof 90-minute rated storage cabinet, but there's no exposure risk under standard operating conditions. You could be filling a beaker, so you're doing a transfer from a large bottle to a small bottle. There's low risk, but there could be some exposure there, and you want to do that transfer inside some sort of containment device, but it's not a high risk of exposure. And then you could be heating acetone, and this obviously, being a flammable chemical with a very low flash point, is a very high exposure risk. And God love the internet, I went out and I searched heating acetone, and this is one of the very first photos I found, and this appears to be a burner on someone's kitchen table with some acetone bought at a hardware store and a fan to blow over it, and it looks like at least they're heating water to then warm up the acetone, but by gosh, this is done on an open bench, so please don't anyone ever do anything like that. Definitely heat it with water, not directly, but and I'm not the chemist here, but that scared me when I saw that. So the point here is to study the risk in context of how that's going to be used, right? This same product, same chemical used three different ways, or storage is hardly a use, but it's in your building. So from storage to dispensing to heating, and it's the whole spectrum of possible risk. And it's a great slide. Thank you, Cedric Harry, for that. So I do want to go back, though, to the fundamentals in determining controls. So the U.S. National Institute of Occupational Safety and Health, or NIOSH, they've published the hierarchy of controls along with CDC, our Center for Disease Control. And the very first thing you want to do is eliminate, if you possibly can. The most effective is in blue, eliminate that risk, right? Remove that hazard from your laboratory. Don't use that chemical. Don't do that process. But that's not always acceptable. So the next most effective is to substitute it. Find something less hazardous to use to get the same result in the end, if possible. But that's not always possible either. So then you involve engineering controls, where you really want to isolate the people from the hazard, or the hazard from the people, depending on how you want to look at that. And we all know about those. Fumehoods, obviously an excellent example. Biosafety cabinets also. Glove boxes at the extreme, or isolators. Usually with that, though, you're going to need some administrative controls. You're going to need to change how people work with those engineering controls, make sure they understand it through training and how to properly use it. They may not understand A to Z, meaning from opening the sash of a fume hood all the way up to the exhaust on the roof, but they at least need to know how to use that engineering control properly and safely. That is less effective, obviously, so you want engineering controls that are just as intuitive as possible with the least chance of misuse. And then lastly, PPE. If you can't do any of these others, if you can't eliminate, substitute, or there is an engineering control or administrative control to help, then you need to obviously protect the worker with personal protective equipment. And that's not always the most effective either. People tend, like myself, to have their mask maybe down around their neck instead of up over their mouth and their nose, and so forth and so on. So again, just back to the fundamentals, this is how we should always approach a hazard or a risk. So when we assess that hazardous, especially chemicals, when we assess those, we want to find the resources that allow us to understand what the exposure limit values are. So the safety data sheet, NIOSH, product labeling, obviously the internet you can find, and it's going to vary depending upon the region in the world. And it's great that we have an international audience today. And Heidi detailed a lot of the differences and similarities in some regulations. Same thing here. So in all regions of the world, we approach it from both a short-term exposure limit and also a long-term exposure limit, right? We have, we're just using 3 different examples here, France, US, and Germany. And then if we look at, let's say, just randomly picking chloroform, you'll see that short-term exposure limits 50 ppm in both France and US. However, in Germany, they're much more strict with their maximum concentration exposure of just 1 ppm on short-term. And then if we look at the long-term exposure, so this is 8 hours a day, 40 hours per week for 40 years of your life. In other words, a working lifetime exposure limit is 2 ppm in both France and US and half a ppm in Germany. There's a large difference between those, and obviously you want to choose the lowest value published, I think anyways, and that's how we approach it at ERLAB. So even though possibly you could be exposed to 2 ppm in the US, we would look at it as a half ppm limit. Formalin, obviously this has gone through a lot of review and change over time here, and it continues to come down and come down and come down as it should. And here again, Germany leads the charge with the least exposure, the lowest exposure limit on the long-term exposure. As far as acetone, 1,000 ppm, we seem to agree globally is your short-term exposure, and 500 to 750 is your short-term exposure. So we would use both France and Germany in that case. And then lastly, my last example, methanol. This one's all over the board, from short-term exposure limits that don't agree with each other, but at least on the long term, we certainly all agree that the maximum exposure of methanol would be 200 ppm and an 8-hour day, 40 hours a week. So this is how we assess the risk. We choose the lowest possible. Basically, it's the most difficult to achieve, quite frankly. So product labeling. So we've talked about safety data sheets a bit, and I'll get into that and more, but obviously on the product, you will have those pictograms that we all know. And the first one, the carcinogenic, mutagenic, and reproductive hazards, right? These are right at the very top of the list, the most hazardous. You could have cylinders under pressure, so you're gonna have to handle those properly, store those properly, move those around the facility properly. It could be explosive, so again, you get into storage and handling. Hopefully you don't have too much of that in your building. Harmful or irritating, always good to know and to deal with properly. Corrosive, whether it's an acid or a base, you're going to have corrosive concerns there. So in the proper PPE and handling or containers when you dispense that. Combustion, obviously always a concern from the flammables. Flammables, right? So it's not just flammable, it's combustion. Again, I'm the HVAC guy, I'm not the EH&S expert, but they both are concerns. Dangerous to the environment, you don't want to release these obviously into the environment as much as possible. I'll talk more about that later when I compare ducted hoods to filtered hoods. Acute toxicity, so the first and the last, these are the chemicals that there is no taking it lightly at all. Not that you would take any of this lightly, but these are the ones we're definitely highly recommended to use a glove box or isolator to maintain maximum containment and separation between personnel and the hazard itself. Okay. So which dangers to evaluate? Safety data sheet has 16 chapters, and as Dimitri said earlier in the question and answer of the previous session, I absolutely agree. The SDS has gotten much better and really filled this out. I started to highlight those that I thought, exposure control, number 8, chapter 8, physical chemical properties, number 9, and I realized pretty soon I was highlighting all 16 sections. They all have importance to evaluating the hazard, so you really do need to review the entire safety data sheet to understand the hazard. And I just chose one very quickly, and it was 7 pages long, and I know there are some that are even longer than that, but all of this is very important to evaluating and understanding the danger or the hazard that that chemical presents. And you have to do this, of course, for every chemical. So our methodology, when we look at assessing the risk, first thing, obviously collect all the safety data sheets, right? We need to know what's being used, in our case in the Fumehood, it could also be a biosafety cabinet or other. So the names of those products, the suppliers, the pictograms, the dangers, the warnings, all the cautionary advice that is contained in that safety data sheet, you need to collect all that information, understand that, and obviously comply with that. Now you can evaluate the total or the gross risk by looking at it and understanding and prioritizing the quantities, how often, the frequency, how long, the duration of the use, and the hazardous classes. And then you can look more precisely at the net risk assessment by understanding the exposure and the modalities of that exposure, the level of collective and individual protection, and organizational function. So this is where we really get down to working with a client and understanding their risk of using that chemical in their facility the way they do. And so once you know these and you go through this assessment process, you can then choose your technical investment, right? So which safety equipment will you purchase? What process changes do you need to make? And then you also need to do, and so that's your engineering controls, sorry, if we go back to the fundamentals. You also need to improve your organization. That might be a controversial statement. Maybe you just make sure the organization is fully aware of this new hazard, right? So this is through training and awareness, also monitoring, measuring the use, the proper use of that equipment. Those are your administrative controls. And so again, going back to the fundamentals, you have your engineering controls, your administrative controls. So we've done the risk assessment, now it's time to choose your safety equipment, right? If we understand that risk, you understand what you need to do and to what level you need to do that. There are multitudes of types of exposure control devices, ECDs or exposure control devices as we call them here in the United States. I know there's many different acronyms across the globe, but we're all talking pretty much the same language. So first couple examples, chemical fume hoods. Chemical fume hoods provide personnel protection only. They have that constant draw of room air into the enclosure so that they keep the hazard, the dust, the fumes, the vapors away from the user. They do not protect the product, and in some cases they do not protect the environment. In other cases they also protect the environment using a filtered or a ductless type enclosure. Biological safety cabinets, they offer both personnel and product protection plus the environmental protection because they're HEPA filtered internally. And here that's for the use of biological hazards only. This is not a chemical fume hood. And a chemical fume hood is not a biosafety cabinet. They are two completely different animals. Even if they're both filtered versions, they have different uses for different hazards. The ventilated safety enclosures, these come in all sorts of different forms, and this is really just minor use, nuisance odors, personnel protection. This is what just popped up on the screen is a small little ventilated enclosure that goes on the work surface in a teaching type laboratory, an undergraduate low hazard teaching type laboratory. It still is exhausted and ducted to the outside, needs fans and HVAC, but low cost. Not a chemical fume hood, doesn't have services, gas, water, vacuum, that sort of thing. Then you get into the highest degree of personnel and truly product protection also. We have a complete barrier, total separation when you have your glove box or your isolator as shown in the bottom middle picture there. So this is, except for when you're transferring product in and out of the glove box, this is total isolation between the users. And hopefully you do those transfers properly and you maintain that total isolation. And again, this gets back to the CMR and the high toxicity products we were talking about earlier. And then there's a whole host of other solutions, right? Whether they're snorkels, extraction arms, elephant trunks, call them what you will, pathology workstation is in the lower left corner there, canopy hoods, similar to the hood over the range in your kitchen or my kitchen, just drawing some air and hoping to remove a nuisance odor. In many cases, these do not provide the level of protection of a biosafety cabinet or a chemical fume hood, so you really have to make sure they're the right product for that application, and I'll talk a little bit more about that later on. Each ECD has a very defined use. The manufacturers can tell you about that. Obviously, there's industry experts, and you know also. So utilize all that information to make sure you're choosing the proper one for your hazard. It has ergonomic and operational constraints. Biosafety cabinets generally have a chair in front of them. You're seated. Fume hoods, you're generally standing. That may or may not work with the users. They may have their own needs to make sure that ergonomically they can properly use that. And then operating costs. After choosing safety, always safety first, operating costs need to be understood. I'll talk more about the different versions, for instance, of chemical fume hoods in a couple slides from now, and you'll understand what that impact can be. And so let's get to that. So chemical fume hoods, the goal here again is personnel protection from vapors, gases, dust, fumes, It does not protect the product that's inside the fume hood in any way. And they're available, and again, another myriad of options here. And basically, if we break it down into two main characteristics, it's either an airflow change or a physical change, but there are also versions that change both. And so from an airflow perspective, the very first fume hoods were, the very first fume hoods were fireplaces hundreds of years ago, and then we got a little bit better, and they were constantly exhausted the same volume of air. Once we had electricity and fans, we were just always drawing the same volume of air, and that's called the constant volume bypass hood, right? And so shown in the lower left of the screen, those two diagrams, the far left, the sash is wide open, and so all the air is entering. These are side views of fume hoods. All the air is entering through that open sash, or the vast majority of it is, if we want to be technical. But then in the middle there, the middle left, the sash has been closed on that constant volume hood, and that opens the bypass area above the sash. So the air from the room now comes in and mixes with the air in the fume hood and is exhausted as usual. And so that is bypassing the sash. That keeps the face velocity not too high down at the bottom of the fume hood, but it's simple controls. It's simply one fan on the roof, just exhausting the same amount of air all the time. The problem is it's extremely high operating cost in many cases. Not always, but in many cases. So along came another change about 1985 or so, where we went variable air volume. So as you close the sash, you reduce the air. There's an airflow control device now attached to the top of the hood somewhere in the ductwork, and a fan that can speed up and slow down appropriately. And so here we're saving energy and always maintaining the proper face velocity on that hood, and thus, hopefully, the proper containment of that hood. Then there's a whole host of physical changes and options. Floor mounted. We used to call these walk-in hoods in the United States. It's the last thing you want to do is to walk into a fume hood. So we changed our verbiage to a floor mounted. If there's a large cart or a large container, a 55-gallon drum, and you need to roll that into a fume hood, you would need a floor-mounted hood. It has multiple sashes that go all the way down to the floor. There is no bench or work surface in the middle of the hood. There's specialty hoods for distillation, radiation, acid digestion, perchloric acid, very specifically hazardous and explosive once it dries out and crystallizes. Those are all made physically, specifically for those applications. And then there's others that impact both the airflow and the physical natures of that. So ducted versus ductless, or filtered, as you'll hear me say back and forth. Auxiliary air, I happened to see a few of these the other day. They have been discontinued by most manufacturers, and I never encourage anyone to use an auxiliary air hood. That's where untreated or semi-treated air would be introduced right above the sash, blowing right down on the user. So it's a very uncomfortable experience in humid summer air or cool winter air, and it also affects containment of the fume hood, so we've walked away from that, but you might still see some out there. Proceed with caution if you choose to use auxiliary air. Ducted fume hoods, in case you don't know, sometimes people are amazed by this, almost all the time, just fully exhaust that contaminant to the outside. There is no treatment, there's no filtration up on the roof. There are times when there certainly is, but the vast majority of ducted fume hoods are just exhausting to the outside. And so how that looks from a building perspective, and again, another side view of the fume hood here, you've got a fan that's somewhere up on your roof. It should not be within the building. The exhaust ductwork and the flow should always be under negative pressure. Somewhere down lower than that, you've got some sort of airflow control valve or damper, and that is what's setting that airflow appropriately for that sash position. Then, of course, at the bottom in your lab, on top of the bench here, in this example, you've got the fume hood enclosure. It has a rear plenum. It has that operable sash. It has the airfoil down in the lower front. That helps the air come in and direct it to clean and sweep the work surface. So you have to choose these, if we get back to risk assessment here, based on the standards and compliance with standards in your areas. The manufacturers will tell you which tests they've conducted on their fume hood enclosure, and you need to comply with the regulations in your region. So if it's France, it's NFX 15206, or it could be EN 14175. If it's here in the United States, it's the ASHRAE 110 containment test standard. And it's always done, the containment test is done in the normal operating flow, not abnormal conditions. If a fume hood does not have airflow, it cannot contain the vapors. It's just that simple. So the fume hood is very much dependent upon everything connected to it to make it work. So what about after installation, right? So it's important that air is always there and it's always exhausted or filtered and returned to the lab, depending on the type of hood. If it is exhausted, you must have makeup air. You cannot exhaust what you do not make up back into that laboratory. And that's where that high operating cost comes into play. And then always, if you are exhausting that fan on the roof, pay attention to possible re-entrainment, that exhaust air could somehow mix and come back into the building, either through open windows, HVAC inlet systems, or even a downstream building just across campus. That concentration, it will be diluted and hopefully enough for no hazard, but it will and it can progress across the campus and possibly be re-entrained in your building or someone else's building. And the cost of operation of that ducted fume hood is that exhaust air, plus more importantly, quite frankly, the heating and air conditioning of the makeup air. That's where the big operating cost comes into play. But there are times when you absolutely must exhaust it. It must be a ducted hood. We understand that. Here, from a laboratory to a building view, this is what's going on. I think we probably all are aware of this, but in case not, that makeup air has to be heated or cooled depending on the season and where you live. And sometimes both at the same time, cooling it to knock out the moisture and then reheating it because they made the air too cold to begin with. But at least now it's dry and you'll be comfortable once that is further humidified or dehumidified, filtered and brought down to the laboratory. The air will go out the fume hood, whether it's VAV or constant volume, a certain amount of air is always going to flow out of that fume hood. And then where it says mechanical ventilation on the right side of the lab, you'll have some amount of the air in the room also serving as sort of a general exhaust, as we call it, to maintain proper pressurization. So the fume hood is the primary containment zone. Part of the risk assessment, the laboratory almost always is negatively pressurized. You exhaust slightly more than you supply, so that it serves as a secondary containment zone. If you have a spill outside of the hood, if you have a spill on the open bench, you have odors, they'll be contained into that laboratory unit only and not spread throughout the building, hopefully. Ducted fume hoods, test standards vary across the globe. I touched on this briefly previously, but EN 14175 has many different chapters and versions, all depend on the standard itself. I'm not experienced with 14175, but I think you can see that it covers all of that, how to test properly. It is a test standard for ducted fume hoods. In addition, in France, there's NFX 15206 for the thresholds for containment. And in the United States, we have similar. We have ASHRAE 110, which is the test method and the thresholds for containment tests, whether it's at the manufacturer, as installed, or as used. So there's different thresholds based on the test being conducted. And another one I'm aware of, and there's many more other than this, obviously there's a whole set of standards in Asia also, but I work on the CSA committee, Z316.5. I just released a 2020 update to theirs. Same thing, how to test properly a ducted fume hood and the thresholds for that containment test. Because a fume hood, it's really about containment. Will it contain those hazards, right? So how do you conduct that? Very quickly, just talking about face velocity. For those that don't know, EN 14175 sets up a grid pattern. You have to be within 100 millimeters of the edge and then 400 millimeters between test location or less, depending on the size of your hood, right? So you use these rules, you measure at these grid points, you data log all that information, and then you look at the average face velocity of that fume hood. As another example, and there's many more, is CSA. So up in Canada, you actually set up also a grid pattern, no greater than 330 millimeters, and you test in the middle of that grid. So it's different, and it's significantly different. And these two don't fully agree. That's okay. That's what happens. But I think you would find that if we conducted both of these tests on the same hood, we would get very similar results. That it's sort of the accuracy is worked into the test standard and the method of test. So always using a hot wire anemometer, a single direction hot wire anemometer, so you can measure the air coming in at each one of these grid patterns. It's not done with a handheld, it's actually on a stand. There's not a human standing in front of it interfering with the airflow. It's there fixed. CSA, for instance, you must take 20 readings at each location and average those. Make sure that anemometer is recently calibrated, but of course, and only a few countries define minimum face velocity. Face velocity is easy to measure in the field, meaning in the installation. However, again, containment is what we're most concerned about. Face velocity is an indicator that everything is working properly and that you should be able to achieve acceptable containment as long as you maintain that proper airflow, that speed of air entering into that fume hood. So we look at a ducted fume hood in the EU. The containment principle is a tracer gas, usually SF6. This is changing, at least here with ASHRAE 110 test standard in the United States. We are changing away from SF6 given its very high global warming potential, and soon we'll be using vaporized isopropyl alcohol, IPA. But you release that inside of the fume hood at a known rate, and then you measure along the plane of the sash. And there's multiple different protocols, the internal plane, the external plane, the robustness of all that. You really have to follow your regulations in your country. There's no limit value in the European standard, which I find interesting, but here ASHRAE 110, also CSA 316.5, the as manufactured test. So the manufacturer has a test laboratory, the fume hood manufacturer. They install it under ideal, absolutely perfect conditions, of course. It's their product, brand new in their test lab. It doesn't get any better than this. There's no humans, there's no users, there's no loading of the fume hood yet. So it must contain at the highest standard, and that is 0.05 ppm detected outside the fume hood, right? So otherwise everything else is contained. Once that fume hood is installed in the actual installation, in the laboratory, in the new building or the renovated building, you're no longer in absolutely ideal conditions. The supply air might be a little bit closer to the fume hood than you would like, but it had to be there. The fume hood might not be in a perfect location. It might be a little closer to a door or a window. There could be thermal drafts in that. So it's allowed to increase to 0.1 ppm as installed in the field. And I agree with that methodology. That makes sense to me. So changing to the next type of containment device, again, once you know the risk, you've done the risk assessment, ductless filtering fume hoods. Are these appropriate? Could these be used for your risk? For some things like CMRs and the highly toxic chemicals, no, immediately not. This isn't even considered for those sorts of applications. But for others, for low dosage and lower risks, yes, we can certainly look at the use of recycling the air. So the fans and the filters all right directly on top of the fume hood, clean that air and return cleaner air to the laboratory than actually went in the open sash to begin with, never mind the chemistry being performed inside that fume hood. And total safety is both the containment factor of the fume hood enclosure, whether it's ducted or ductless, plus the filter efficiency. So obviously you want to make sure that the filters are the appropriate filters and have the efficiency needed for this specific application. And can also include HEPA filters. Generally, it's mostly 2 layers of carbon filters, but it can also include HEPA if you're working with hazardous particles or solids. Obviously, without exhausting all that air, you do not need to make up all that air, so that lowers in many cases, but not all cases, but that will lower the energy cost. But you do have to include the cost of changing the filters. So a hazardous risk assessment for ductless hoods includes the life of those filters, not just if they'll capture and contain everything that you're using, but will they last long enough? Multiple standards across the United States regarding recirculating fume hoods, AFNOR NFX 15211 in France. Obviously in England, we've got the British standard 7989, China, the JGT. USA, we have here our ANSI-AIHA-ASSP. We gotta put a 3rd or 4th group on that one. Z95 is our ventilation standard. They include ductless fume hoods in that. Also, CIFA 9, it's a recommended practice, not exactly a standard, but it does get specified. CIFA 9 is a manufacturer's group, scientific equipment furniture manufacturers, and they've got a recommended practice for using ductless fume hoods. And then in Canada, Z316.5. And you can see in Europe, it's in preparation. And Dr. Cedric Carey of ERLAB is on that committee, and we're getting close to release, I believe, of the new European standard for recirculating fume hoods. Until then, NFX 15211 still applies. So the front air velocity, pretty similar to a ducted fume hood. You still need to look at that and make sure you've got the right velocity entering that fume hood. That doesn't really change, other than There are limits to the filters. The air can only flow so quickly through the filters, so the face velocity set point might actually be lower. And that's okay as long as that fume hood contains, because it is about containment, not velocity. Containment ultimately is what you truly want to measure and what is most important. The two are linked. Without velocity, you won't have containment, but you could have too much velocity and not enough containment. So there's a whole test protocol for that, looking at the internal plane of the fume hood and the threshold limit value, 0.1 ppm of the SF6 tracer gas would be the standard there. However, SF6 is one of those lightweight molecules that will go through filtration. So if you do not, for the test anyways, do not duct your ductless hood, follow me there hopefully, then that SF6 will come back into the laboratory and invalidate the results. So we do have modified test procedures so that you can generate IPA in the field, and ASHRAE is actually changing, ASHRAE 110 standard is changing to that test protocol in the next year or two anyhow. So that's good news. Now, you want to choose, obviously, filters that are appropriate for the application, whether it's just solvents you're using or if you're also possibly using acids and bases. And there are filters, there are many different types of filters from different manufacturers, and you want to make sure they've been tested for your application and the chemicals you're going to use. And the way to do that properly, as shown in this diagram here, is to generate a known concentration within the fume hood enclosure and then measure the air coming off of the filters, off of the top of the fume hood, and it should be less than, or needs to be at all times, less than 1% of that TLV, threshold limit value. We spoke earlier about 4 different chemicals from chloroform to methanol of the short term and the long term. I'm talking about the long-term exposure limit. So that very small value to begin with, now you want to be less than 1% of that, just to absolutely guarantee and maintain safety. That is the test standard of NFX 15211. This is how it's conducted, and this test is conducted inside a bubble-tight enclosure so that you're not having dilution of whatever contaminant may eventually make it through that filter. This is a very tight test, a very exacting test, and it's exactly what you would want when you have a ductless or filtered fume hood in your laboratory. Compliance, make sure the manufacturer of your ductless hoods is in full compliance and has certificates from independent third-party test companies that we comply fully with these different standards depending upon where you are. Makes perfect sense. The same thing for the fume hood enclosure. This is for the filtration, but the same applies to the actual enclosure itself. You want to make sure everybody's been tested properly to the standards in your region and has passed that with third-party testing, not just their own testing. Very important. So when we speak of filtered or ductless hoods, one thing I do want to bring up, obviously, is the sustainability, and that's part of my presentation here today. BR+A Consulting Engineers in Boston did an excellent review of basically everything included in both a ducted fume hood, and manufacturing and shipping and installing that, versus a filtered fume hood. And when I say everything, I'm talking about harvesting the coconut shell to begin with, the energy needed for that, to activate that carbon so that it will absorb all the chemicals, to transport that carbon around the world depending on where it comes from and where it's going. We looked at specifically Boston in our example because we did a zero net energy laboratory in Boston using filtered fume hoods. And in the end, what it comes down to when you look at the 20-year operational life cycle of a fume hood is a 94% reduction in the carbon footprint. I mean, a dramatic reduction in the end. This includes replacement filters. This includes a lifetime of both different options in using them. You avoid all that gas for reheating the air that's coming in during the winter. That makeup air, you no longer need as much of it. You avoid the electricity of running all the compressors and whatnot during the summer to cool that air, if you're lucky enough to have air conditioning in your building during the summer. And so that's the benefit of using a filtered fume hood. But it has to go through that risk assessment. We do not short cycle the risk assessment at all. It has to be fully approved for that application in your specific laboratory each and every time. So other safety devices, I did promise to review very quickly some of the other safety devices that are out there. Glove boxes, isolators, so again, total containment, but it's extreme. It's very difficult to work with an isolator. It lives up to its name. It isolates you from what you're trying to manipulate. So it has to be loaded properly, already in a container. Your sample then goes through a loading door. You have to seal that off. It's under negative pressure in case there were ever a leak in one of the gloves. This is a negatively pressurized glove box because the gloves are being sucked in, if you will. If it was a positively pressurized because you didn't want to contaminate something, the gloves would be sticking out. There's great pictures of both of those out there. It comes with a very high price. This is maybe not always a custom build, but it's certainly a custom review each and every time to make sure you're getting the right piece of equipment for your needs. And you need that downstream, upstream filtration. Just a lot of cost, a lot of isolation. But again, if you're working with the CMRs, the highly toxic, immediately lethal stuff, you have to work with one of these, or highly recommended anyways. Snorkels. This is the opposite end of the spectrum. So this is now, you're working with more of a nuisance odor or a heat generator in a lab. I recommend these for capturing heat, spot capture of heat, or again, nuisance odors that are not a hazard, that they're well below your threshold limit value, your exposure. It's just nuisance. Oh, I don't like that smell, but it's not going to harm me. These absolutely do not replace a chemical fume hood. I've unfortunately seen some installations where a snorkel was used because they couldn't fit a fume hood and they thought, well, that's good enough, and it's not. Even with the very wide bell mouth on the end of the trunk there, you must keep it so close to the product you're working with that it's almost an isolator in itself. It's hard to see the product, hard to work with the product. Most of the time I see snorkels lifted up, left up, high up in the ceiling and not even used, which is even worse, of course. So please don't replace your chemical fume hoods with snorkels. And then lastly, biological safety cabinets, many different types, 3 different categories, different types within each one of those. I'm not qualified to speak about biosafety cabinets, but the manufacturers are very reputable. There's very strict rules and standards for these, EN 112-469. There's also NSF 45 here in the United States, National Sanitation Foundation. So very strict standards. Manufacturers can help you out with selecting the appropriate one there. There's ductless versions, there's ducted versions. There's some that can use small amounts of chemicals, but here again, they do not replace chemical fume hoods. So if you need to do chemical manipulation, you would do that in a chemical fume hood, not a biosafety cabinet. If you need to work with biologicals, you would do that in a biosafety cabinet, not a chemical fume hood. And don't forget that the biosafety cabinets do provide protection of the product. So the product will not be contaminated by the user or any contaminants in the air inside that laboratory. It's a HEPA filtered downflow inside of that enclosure. So when it comes to the use of any and all safety devices, obviously it has to be done properly, right? So as seen here on the right, Marie is leaning way too far inside of her fume hood. Do not stick your head inside of a fume hood unless it's brand new and has never been used. Otherwise, keep your head, keep your breathing outside of the fume hood, of course. So proper installation, the proper use of the device, and then that's good at the start, but we need to maintain that. So the proper testing annually and the proper maintenance continually of that fume hood. It is not a storage cabinet. Lower left picture here is just a completely misused hood. That is a fire waiting to happen. That's just not good at all. A lot of hazards shown there. Store the chemicals in the appropriate storage containers after their use. Do not leave them in the fume hood unless you're going to immediately use them. So in conclusion, you want to get the maximum protection, obviously, during that manipulation of any chemicals, and you don't want to oversize your containment device, though, because then you're going to lead to too high a cost and too high an energy operating cost. So again, you must do that risk analysis first and then choose the appropriate device. Now that device could be chosen to be a higher level of containment because eventually you'll need it. You don't maybe need it immediately, but you will in the future. That's understandable. And then obviously respect those good practices for using that equipment appropriately. That comes back to those administrative controls and making sure that that risk assessment is understood and the training program is there for new users and continual retraining. If the users of fume hoods are like me, they tend to forget things over time if they don't do it continuously. Monitor that equipment, inspect that equipment, maintain that equipment continually, and then obviously at least every year have a third-party inspection of each of your containment devices and certify that. And depending upon the risk, you may want to and need to do that more often. In some cases, the extreme case, before each use. And that's really up to the individual situation. And that's it for me today.